So in this video, I want to just talk a little bit about how Grignard reagents are formed in terms of the mechanism. And this is not a mechanism that you would need to know. So if you're pressed for time, then skip past this video. But I wanted to show you this just because I don't want to show you, I don't want you to I don't want to just give you information and say, trust me. That would be teaching you the opposite of science. You should be constantly mistrusting me, demanding to understand things and see things for yourself. And so I don't want to say, okay, when you plop, I mentioned in a previous video, when you take an alkyl halide and you plop solid magnesium into it, and it's like magnesium strips, like you could buy at Home Depot or some store, some hardware store. When you do that, the magnesium inserts itself in between the carbon and the bromine. But how does that happen? Why does that happen? That's what I want to talk about in this video. And again, this is not a mechanism that you will be required to draw. I just wanted to show you this so that you can sort of follow it. Now, as you might remember from last semester, anytime you have a metal, the mechanism for it often involves radicals. Because metals have very low electronegativity, they can lose one electron relatively more easily than another element could. And so that's how this mechanism starts too. This is going to be a radical mechanism. Remember that a radical is an atom that has an unpaired electron. It's really unstable because electrons, a single electron is like a little bar magnet. Anytime microscopic on the subatomic world or the macroscopic world, anytime a charge moves, it creates magnetism. And so these electrons are moving at around 4.5 million miles per hour, and so they act like little magnets with a north and a south side. If one is all by itself, it's really, really sticky. It's going to stick to the first magnetic thing that it comes across. And that's a lot of things in the world. A lot of things have that feature. If it's paired up with another electron, well then the little magnetisms of the two electrons can sort of cancel each other out, the north side and the south side of each one, and so it's more stable. But when you rip them apart, you force electrons to be unpaired, then you get a really reactive species. It's called a radical. Okay, so magnesium, solid magnesium metal, has a whole bunch of electrons on it. Let's imagine magnesium is in group 2A. Let's imagine 2 of all the electrons around it. It has 2 valence electrons. And when you put that into solution, this bromine is really electronegative. Even in this bond, it's pulling electrons to itself, so it becomes slightly negative. The carbon becomes slightly positive. And when this molecule, which is bouncing around violently, smashes into magnesium, these electrons feel the pull of that electronegative element. It's more electronegative than the magnesium is. And so what'll happen is one of them will get ripped off and go onto it. And so it will literally jump from the magnesium to the bromine. Now remember, this is a fishhook arrow. Whenever you draw radical processes, you draw a fishhook arrow. That curved arrow always shows the movement of electrons, and the head only has one head here, right? Compare with a normal arrow, it'd have 2 heads. Here we only have 1. You may not have realized the heads of these curved arrows are significant. They tell you how many electrons are moving. So if you have 2 heads, then you're moving 2 electrons. Here, we're just moving 1, so there's only 1 little hook there. And the arrow on the whole is called a fishhook arrow. So what we get after that is this same molecule, but the electron will have moved. So one of these electrons is going to move, it'll go onto this bromine, and now the bromine, and here I'll draw in the other lone pairs that were on the bromine originally. Now that bromine is going to have a negative charge, a full negative charge on it. Because it gained an electron, and the magnesium will have a full positive charge on it because it lost an electron. So this unpaired electron is really, really unstable. And what it does is it steals an electron from this bond nearby to stabilize itself, right? This is like a really sticky magnet. And so it's pulling on all of the electrons nearby, because all the electrons nearby are like other little magnets. So this is going to pull the electron, one of the electrons in this bond towards it. So one of the electrons in this bond will go and pair up with that radical, that unpaired electron, and the other one will go on that carbon. So notice, two fishhook arrows, there are two electrons in this bond. One of the electrons goes onto the bromine to stabilize that radical, and the other one creates a new radical on the carbon chain. The magnesium, for now, is standing aside. Right? It's a metal, so it can spread the electron and the charge over that ocean of nuclei in the metal. In a previous video, we talked a little bit about how metals are sort of like plasmas, where the electrons aren't tied to one individual atom. They're coursing over a sea of nuclei. And so by spreading that out, by spreading the electron out over all of the nuclei in the chunk of the metal, this can become more stable. And so this happens first, before this reacts. Okay, so after that step, what we have is our two carbons, and now there's a radical here. That's that one electron that went from the bond. We also have a bromine, and the bromine now has all paired electrons, full negative charge still, and we still have our magnesium. So these are the pieces. Now, with all of these things knocking around in solution, the magnesium radical pairs up with the carbon radical. Those are the two most reactive species here. Remember that bromine is really big. Chlorine, which is smaller than bromine, chlorine is the size of a methyl group, CH3. So it's as big as 4 atoms put together. Bromine is even bigger than that. As you go down on the periodic table, the atoms get bigger, and bromine is below chlorine. So it can take this negative charge and spread it out over an enormous space. And that effectively dilutes it and makes it less reactive. So this is, relative to these radicals, this is less reactive. So these now pair up. So the carbon contributes its one unpaired electron, the magnesium contributes its one unpaired electron, and you form a new bond. Or let me actually put this going down. You form a new bond between the carbon and the magnesium. Magnesium still has a full positive charge on it, the formal charge there. And if you want, you can use that formal charge equation that we've discussed previously in the videos, and you can calculate that for magnesium and see that it's a positive one. So now we have that species, and the bromine is still knocking around, and you could see what's going to happen next. This negative bromine is attracted to the positive magnesium, and so these electrons sort of stick to this. And it's not really a covalent bond, they just ionically are attracted to it. And so that's often written just as MgBr. So this is sort of an ionic compound, and this is a really polar covalent bond, because the magnesium has very low electron negativity, so it gives its electrons away. Whatever it's bonded to gets it. In this case, that's the carbon, and so you get those charges there. And the truth is that bond is so polar that you could almost treat it just as so it's like almost equal to as a completely and purely ionic bond. That's often how we're going to draw it in these mechanisms. So that would be as if the carbon had all the electrons all the time, full negative charge, and the magnesium had the full positive charge there. So you can see that that magnesium inserting itself really happens through, a radical mechanism. Magnesium gives away one electron when it bumps into the halogen, or the bromine, usually, of the alkyl halide. That makes that bromine a little unstable, so it steals one electron from the bond nearby, and that causes it to leave as a leaving group. And it creates a new radical on the carbon that was bonded to the bromine. That radical pairs up with the magnesium radical that was created. And then that's electrostatically positive and negative charges attracted to the negative bromine. And so you get your Grignard reagent. And so then you can use that as a carbon nucleophile. So again, this is not related to a test question or to a homework problem. I just wanted to provide this in case you were curious and you wanted to know the reasoning behind things. I don't like ever telling you to trust me. In a science class, you should be distrusting me as much as you possibly can. That's what it means to be a scientist.